All right, so now what we have here is one overall point of view on all these theorems. And on the other hand, each of these theorems can be applied and related to something we saw in the past. So let me now go into those aspects of relating this to the line integrals. And I will mostly focus on understanding of something about those integrals rather than on computing. I wrote somewhere in the file that I would think there are two basic applications of the fundamental theorem of calculus. One is for computation, and the idea is that if you want to compute a double integral, it helps you to reduce it to line integral, which is conceptually simpler. Because after you parameterize, it has only one variable to deal with, as opposed to two variables. But that's the computational aspect. I'm not very interested in simplification of computations. I would rather talk about understanding that we can gain after knowing all that. So let me erase some of this, unless you have some questions. So let me relate it first to the work of the field of forces. Because I already applied the previous version of the fundamental theorem to the work of field of forces, and we figured out that if the field of forces has the potential function, has potential energy, then the work is very easy to compute, and the work doesn't depend on the path that you follow. Now, let me go back to that work formula. So I have that work equal to an integral along the path of the dot product of the force with the velocity vector, and I integrate with respect to time, and I do it over some path determined by some position function f of t. Now, the question is, can we relate this integral to anything about fundamental theorem? And if yes, what would the fundamental theorem say about work of field of forces? How can it help us understand better the work of field of forces? So that's the question, but then I have to relate this formula to that formula. And the way I would relate it is, I would like to relate it to the curl version, to the Green's theorem. And the first thing I need to do, and of course I'm trying to relate it to the line integral, I need to integrate over a closed path. Right? So I cannot understand anything with fundamental theorem unless I integrate over a closed path. So over closed path, the work over the boundary of some region is going to be an integral over that boundary of that force dot v dot dt. Well, this dot means simple multiplication, but this is a dot product. Okay, now I got the integration over the boundary. Now I need the unit tangent vector instead of velocity vector. What do you think the relation is between a unit tangent vector and the velocity vector at the same point? Exactly. So the unit tangent is velocity vector divided by the magnitude. And I don't have that magnitude, but I can make it, right? So I have integral over the boundary of the force dot V, then multiplied by 1 over magnitude of V and by magnitude of V and dt. Now this part makes ds for me, as in the fundamental theorem. And now I have to deal with that part. And remember, this is dot product, and that is multiplication by a number. Now, what I would like to do is I would like to take this multiplication by a number, and I would like to bring it into the dot product. I would like to express this as f dot product with v over magnitude of v. And that's basically the distributivity idea, right? If you multiply two things and then multiply by a number, you can multiply by that number either of those two. The result will be the same. And then this is exactly f dot unit tangent. And I end up with the integral being exactly the same as there. F dot tangent ds. So if I integrate over a closed path, which is in a plane automatically a boundary of some region, my work is automatically the same as that integral in the fundamental theorem of calculus. And now I can apply it and see what it says. So let me apply it here. It is equal to the double integral over the whole region. Now I pass to the double integral. Double integral of what? Of this curl of f. Well, how useful is that? Well, of course, as a computational tool, if someone asks you, well, what is the work needed, well, the work done by a vector field on a given path, well, of course, you would rather do line integral than double integral. Now, the conceptual thing that this fundamental theorem brings you is that, well, this quantity is very relevant to the work. And somehow we never saw this quantity before. Right? It never showed up in the computation when we did this line integral stuff. So, what's important about this quantity? Well, there is very simple observation about double integral. What's the observation? The observation is that if this quantity, which is a function, right? It assigns a number to each point of the region. If this quantity is always 0, then what? Well, then the integral is 0, right? And that's what's called conservative vector field. So let me state it here explicitly. Or maybe I'll move there. I'll need more space. So the statement is, if the curl of the vector field f is 0 everywhere, is constantly 0, then the work over the boundary of any region is always 0, because it's equal to that integral of the curl. All right? So, well, it's not clear how interesting that is. But now let me interpret this in a different way. Just say it in a different way. What am I doing here as I integrate something over a closed path? Well, I follow the path consistently in the counterclockwise direction. And what happens if I change the direction? Well, it's the same thing as in one variable calculus. If you go from A to B it's exactly negative of if you go from B to A. So you will only change the sign if I change the direction. But what it means is that now suppose I go from a point A to the point B. And now suppose I go two different ways. This way and that way. And I ask myself, will the work done by a vector field as I move particle this way be the same as the work done by the vector field as I move that way? And the answer is yes, if this holds, right? So why is this equal to that? Well, because this says as I move there and back, I will get 0. And moving back means adding this work with negative sign. All right? So this statement is exactly the same as the statement that the work is path independent. Right? It doesn't matter which path you take to move a particle. It only the two endpoints matter. But the previous application of a different fundamental theorem of calculus was about concluding that from a different assumption. So the assumption was that if the vector field is a gradient of something for some function E, which is potential energy of the vector field, right? Of some function E. So if it is a gradient, then we have independence of path. So what do we have here? We have 4 different claims about work, right? We have the claim that work is path independent. We have the claim that work over any path is 0, over any closed path. And those two are actually equivalent. Right? So how to go from here to there? If you know that work is path independent, it means that if I take any loop, any boundary of omega, I pretend I pick a point B somewhere on the other side, I can claim that from here, path independence says that integral along this path is actually equal to the integral along that path. But what happens when I integrate over the whole boundary? I will integrate that, and then I subtract this integral, because I'm going backward. So this integral will be 0. So these two are equivalent statements. We are talking about the same thing. The amazing thing is that in the plane, and I'm saying that if the vector field is defined everywhere in the whole plane, all 4 statements are equivalent. They are saying exactly the same thing. Well, let me give you an idea of how to get a function, because this is a very kind of essential statement. Given a vector field, you're looking for a function, for antiderivative, right? And if you look here, then you integrate that vector field along different paths, and you have a claim about those integrals. There is no function coming up. Well, how to get that function? How to extract a function from this path independence? Well, you just define the function. How do you define a function? You say, well, this is my point, call it origin, and let's define E of that function. E of that point is 0. This is my definition. Potential energy at this point is 0. Now, how would I define potential energy at some other point? What's the value? I would take a path from the origin to that point, and I would integrate the work along that path. Well, think about this being kind of zero level, and then I lift something against the vector field, right? And the change of energy is exactly the work done by the vector field. So I define that as integral from origin to A, well, along this path OA of f dot v dt. I define it that way. But then you'd say, well, what if I choose a different path? And I would say, if my vector field is path independent, then no matter how you choose the path, the result, the number is going to be the same. So this way I define what a potential energy is, and then there is a little bit of technicalities to check that if you take this definition and you compute the gradient of this function, you will definitely get the vector field back. Just a little bit of computation required, but basically that's the idea. So all these four statements are the same. And what's the benefit of having all four? Well, because you can use them in different scenarios for different reasons.